In this video, we'll talk about some basic rules for finding derivatives that don't involve using the definition over and over again. The main point here is we want to be able to find derivatives. We don't want to go through the definition every time. We could do that every time, but it takes a long time to do that, and if we have shortcuts for figuring out what the derivative of a certain function is without having to go through the definition, that's going to be a lot easier to use. The first rule we're going to look at is what's called the power rule. That's looking at functions like f of x is x to the n. We've already seen a couple of these before, right? We know that if f of x is x squared, then our derivative is 2x. But we want to see what this looks like for any power, not just 2. So let's just start from the definition and see where that gets us. So we want to find, for this function f, we have that f prime, we can compute from the definition, limit h goes to 0, f of x plus h minus f of x all over h. So I can rewrite as h going to 0, x plus h to the n minus x to the n over h. Now, there's a couple ways you can think about simplifying this out. The easiest, though, might be to rename a variable here. So if we let x plus h be y, and the top here is y to the n minus x to the n. Now, this expression here factors. It's not something you may have seen before, but you can factor y to the n minus x to the n as y minus x times y to the n minus 1 plus y to the n minus 2x plus y to the n minus 3x squared. And then you keep stepping down, y x to the n minus 2 plus x to the n minus 1. If you think about sort of following this out term by term, the first term here gives you a y to the n. Then this term is a negative y to the n minus 1x, but this term here is a positive y to the n minus 1x, so those will cancel out. And the same thing happens all the way down until you get to what's left will be just this. Now, since we've defined x plus h as y, that means y minus x is just h. So, plugging back in the fact that y is x plus h, we get that x plus h to the n minus x to the n equals h times x plus h to the n minus 1, x plus h to the n minus 2 times x, all the way down to this last term, which is x to the n minus 1. What does that give us? If I take that and plug that back in up here, I can now simplify my expression. So we had that f prime of x was the limit as h goes to 0, x plus h to the n minus x to the n over h, but we saw we could factor this to get this as h times x plus h to the n minus 1 plus x plus h to the n minus 2 times x, all the way down to x to the n minus 1 all over h, and now the h's cancel. And when they cancel, I am left with limit h goes to 0, x plus h to the n minus 1 plus x plus h to the n minus 2 times x, powers keep going down, x to the n minus 1. But now I can take this limit. There's nothing wrong with me now sending h to 0. And if I do that, I will get x to the n minus 1 plus x to the n minus 2 times x from the second term here, because all of n minus 2 comes to x plus h, it just goes to x, and then x stays the same, plus all the way down to x to the n minus 1. And there are n copies in here. N copies of x to the n minus 1. Why? Because there are n terms in this expression above, because the powers start at 0 for just the x, they start at 0 and count up to n minus 1, that's n terms. There's n copies here, meaning f prime of x is n times x to the n minus 1. And this gives us our power rule for the functions f of x that are of the form x to the n, f prime, the derivative, is n x to the n minus 1. And that's a rule that we can use to find the derivative of any function that looks like x to the n. It's just n times x to the n minus 1, bring down the power and subtract 1. Now, while I proved this for n that was positive, this actually works for any real number n. The same rule still applies, whether it's a whole number, a negative number, a fraction, all of them still works. This one's great and all, but it only works for certain functions. We also want to know, can we combine these to get rules for more complicated functions? And the answer there is yes, because the derivative is also a linear operator. What does that mean? Well, that means that if I have two functions f and g, and k is any real number, then what happens? Well, I then know that I can add derivatives. If I look at the derivative, if I want to take the derivative of f of x plus g of x, add these two functions together, that's the same thing as differentiating f and then adding the derivative of g. So it means I can basically split derivatives over plus signs, and I'll split over minus signs, and I can move constants outside derivatives. So if I have the derivative of k times the function f of x, this is k times the derivative of f with respect to x. So what this tells me is derivatives play nicely with respect to addition, subtraction, and constant multiplication, which basically means that for any polynomial, I know how to differentiate it. How do I do that? I basically just do each term individually and then add them up or subtract them as they're written in the expression with the appropriate constants. So what do I get here? Well, for f prime, my first term here is x to the sixth, so that should become, bring down the power and subtract 1, 6x to the fifth. For the next one, I have this minus 3 out front, so let's just put the minus 3 there first, and then differentiate the x to the fourth, which should become 4x cubed, subtract 1. I will have a plus 2, x squared becomes 2x. I will have a minus 1 times x, which goes to 1, because if I pull down the power, I get 1 times x to the 0, which is just 1. And 1 is a constant function, so the derivative is 0. That means I could write this as 6x to the fifth minus 12x cubed plus 4x minus 1. And that's my derivative for this function f. There's our first shortcut rule finding derivatives. This lets us solve the derivative for any power function, so x to the n, or once we have linearity, for any polynomial that we just find the derivative of without having to go back to the definition every time. We can use these rules to find the derivative, to get the slopes of tangent lines, or what else we want using the derivative.